Our carbonic acid breaks down into carbon dioxide and water. In our daily lives, carbonic acid is important to maintain a neutral pH in our bloodstream. Carbon dioxide enters the bloodstream and is taken up by the red blood cells. The dissolved carbon dioxide reacts with water to form carbonic acid. When carbonic acid forms, it immediately dissociates into bicarbonate and a hydrogen ion. The presence of both carbonic acid, a weak acid, and bicarbonate, its conjugate base, keeps the bloodstream neutral. A lack of this buffer system can result in conditions such as acidemia with a pH lower than 7 or alkalemia with a pH higher than 7.
CO2 is composed of one carbon atom and two oxygen atoms. Carbon has an electron configuration of 1s2, 2s2, 2p2. Oxygen's configuration is 1s2, 2s2, 2p4. When bonding, carbon is the central atom and forms two sigma bonds and two pi bonds with each of the oxygens. These bonds are a result of the mixing of the 2s orbital of carbon and the 2p orbital of oxygen. This mixing can occur due to the similarities in energy from the 2s of carbon and the 2p of oxygen. The molecule formed is nonpolar with 4 valence electrons, which explains the linear shape shown here. This linear shape means there is no region in which the electrons being shared are unequal. H2O is composed of 2 hydrogen and 1 oxygen atom. Hydrogen has an electron configuration of 1s1. Oxygen has an electron configuration of 1s2, 2s2, 2p4. When bonding, oxygen is the central atom and forms 2 sigma bonds. This leaves 4 lone electrons on the oxygen, as shown here. These lone electrons create a partial charge on the oxygen, and this partial charge is negative and creates a partial positive charge on the hydrogen. The repulsion creates a bent molecular geometry.
There are several types of non-covalent interactions that exist between molecules. In our particular reaction, we had water and carbon dioxide. In the molecule water, there exists a dipole-dipole moment, and that occurs because the lone pairs in oxygen hog the electrons, which causes a disparity between charges, and the oxygen is left slightly negatively charged, while the hydrogens are left slightly positively charged. On the other hand, in CO2, the electrons are all, as you can see, distributed evenly across the molecular space. So there is no no extreme dipole-dipole interactions. However, there still exists, in both molecules, there still exists London dispersion forces because there can be possibilities of temporary dipole moments.
Enthalpy of a reaction deals with the bonds broken as well as the bonds formed. In our particular reaction, the bonds in carbonic acid are broken down while the bonds of CO2 and H2O are formed. The enthalpy values were found from the chart provided, and for our reaction was calculated to be negative 2.2 kilojoules per mole, which shows the reaction is exothermic. The entropy of our reaction was also calculated by the same equation and turned out to be 340.49 joules per mole. Thus, the Gibbs free energy for our reaction was negative 103.72 kilojoules per mole. And a negative value for delta G indicates a spontaneous reaction.